Hey guys, so today in class what we worked on was comparing data distributions. So using the different types of graphs that you've learned how to make, histograms, box plots, and dot plots, and then using what you know about them and reading them to be able to compare them and look at the different stories that they're telling. So what we did for the Do Now in class was everybody chose one of these three graphs, didn't say which one they did, and then shared some information about it. Its minimum, its maximum, and one other thing about the graph. And then the job of everybody else was to try to guess which one they were talking about. So one good way for you guys to do this at home is pause this video here, make your notes on your paper, and then go to someone else in your house and see if they can guess the one that you're talking about. If you can't do that, then I'm going to go ahead and say out loud some information, and your job can be to guess it. So I've chosen a graph, and one thing that I know about it, I'm going to go in reverse order, by the way, from the third question back up to the first. One thing I know about it is that the most common value was 3. The maximum value was 16. And the minimum value was 0. If you guessed that I was talking about the dot plot, you're right. Another one I could do is I could say, I'm going to pick one of the graphs, not saying which one. One thing about my graph is that it's the easiest one to figure out the median from. The minimum is 2. And the maximum is 15. If you think that I was talking about the box plot in the middle, you're right. So remember that the box plot has those 5 vertical lines. The lowest one is the minimum. The second one is the first quartile, which again means that a quarter of the data is between that number and the minimum to its left. So on this box plot, we can see that a quarter of the answers on this survey were between 2 and 5 books. The next vertical line is the median, and that marks off another quarter. So we can see again that a quarter of the answers to the survey were between 5 and 8 books. The next line, the one above 10, is called the third quartile or the upper quartile. And again, it tells us that another quarter of the data is in that section. So a quarter of the answers to this survey were between 8 and 10 books. And the highest number, the highest line, is the maximum, which again marks off the fourth quarter. So again, a quarter of the data was between 10 and 15. One interesting thing we could say about the histogram is that it's the only one that makes it impossible for us to know exactly what any of the values were. Like in the dot plot, we can see exactly how many kilograms were in each backpack because each dot represents a backpack. In the box plot, we know for certain that there was at least one answer to the survey that was 2 books, the minimum, and at least one answer to the survey that was 15 books. For certain, we know those 2 values. We know the minimum and the maximum. But something that we could say about the histogram is that we don't know any of those values. Like if we look at the bar that goes up to a height of 2 between 5 and 10, we don't know for certain what those answers were. They could be 2 people who were 5 years old. They could be 2 people who were 9 years old, or it could be one person who's 6 and one person who's 8. So the histogram doesn't let us do that. But we can still say that the mode age, or the most common age, is between 45 and 50 is the most common range. We could also say that the histogram is not a symmetrical data distribution. So we can see that the box plot is pretty balanced on the left side and the right side. And the same thing about the dot plot. If we ignore that outlier at 16, it's pretty much symmetrical. We can't say that about the histogram because it's not mirrored on both sides. So some potential things we could have said about this. So what we are going to be talking through is looking at 2 different distributions at a time. We're going to do 2 examples. So here, for this one, we have 2 dot plots, and we're looking at the question, do 10th grade students' backpacks generally weigh more than 7th grade students' backpacks? So we can see that some students' backpacks were weighed and they collected that data. They definitely didn't collect the data of every single 7th grader at the school. So we don't know that this is true for everybody or that it represents everybody, but it says they did a random sample. So our hope is that it's pretty accurate data. So go ahead and answer in your head first. Do 10th grade students' backpacks generally weigh more than 7th grade student backpacks? And think of your reason why. So what we're going to do now, while you've got that answer in your head, is we're going to move forward and look at a few other questions that will help us to support that answer. So this question is asking us to think about, did any 7th grade backpacks in this sample weigh more than a 10th grade backpack? Well, we know for certain that most of the 10th grade backpacks were between, well, all the ones that were surveyed were between 10 and 22. All the 7th grade ones that were surveyed were between 2 and 13. So most of the 7th graders that were in this area all weighed less than all of the 10th graders. But we can also see that there's a few 7th grade backpacks that weighed more than at least a few of the 10th grade backpacks. So we can't say that every 10th grade backpack weighs more than every 7th grade backpack, but we can definitely say that the normal area for 10th grade backpack is definitely greater than 7th grade. Now this question is another way that we can analyze this. It says the mean, remember that's the average, weight of this sample of 7th grade backpacks, so we're talking about just these dots right here, was 6 3/10 pounds. So that means that they added up 2 plus 3 plus 3 plus 4 plus 4 plus 4, so on and so forth, and then divided it equally, and found that the mean or the average was right about in here at 6 3/10. The mean weight of this sample of 10th grade backpacks was 14 8/10 pounds. So our question for us to think about is, do we think this is a meaningful difference? Why or why not? So I want you to pause, think about your answer, and then I'm going to say how I would think about it. So now that you've got your answer, how I would think about this. I would think about first, what's the difference between these two values? And if I subtract 14 8/10 minus 6 3/10, I'm getting 8.5. So 8.5 pounds is the difference between the average 7th grade backpack and the average 10th grade backpack. So now that I'm thinking about this data and looking at these numbers here, do I think that's a meaningful difference? I do. And that's because when I look at where the majority of the 7th grade data is, I can see that it's centered over here and the majority of the 10th grade data is centered over here. When you're talking about the weight of a backpack, a difference of 8.5 pounds is really a huge amount, especially when some of the 7th grade backpacks weighed 4 pounds or less. A lot of them weighed 4 pounds or less. So for there to be a difference of 8.5 pounds between the average when some of them were barely 4 pounds, that's a huge difference. So to me, that's meaningful. Now, if we were talking about the mean weight of a sample of men from one country versus men from another country, and the difference between the means was only 8 pounds, to me, that wouldn't be as much of a meaningful difference when we're talking about people who weigh, let's say, 150 pounds on average versus 158. 8 pounds there isn't that big a difference. But here, 8 pounds when you're talking about the weight of a backpack is a pretty big deal, especially when the difference is more than what many of the backpacks weighed altogether. So our last question that we're going to think about with the backpacks and these dot plots is, if you randomly found a backpack that weighed 12 pounds, would you guess that it belongs to a 7th grade student or a 10th grade student, and why? So again, pause, think about your answer before you listen to mine. So my answer to this one, first thing I'm going to notice that there was one backpack in the 7th grade sample that weighed 12 pounds and one in the 10th grade. So we can't just base it on, were there more 12-pound backpacks in either sample? Next thing I'm going to notice is that 12 was the second highest in the 7th grade sample and the 4th lowest in the 10th grade sample. So both were pretty close to the extremes, the 7th grade nearly being the highest and 10th grade nearly being the lowest. But if I had to guess a 12-pound backpack, which one I think it would be, I would go back to that previous information we were given and think about the means. A 12-pound backpack is about 6 pounds away from the average 7th grade backpack and about 3 pounds away from the average 10th grade backpack. So if I found a 12-pound backpack, given that it's closer to the average of the 10th grade backpacks, I would probably guess it belongs to a 10th grade student. So we're going to now look at comparing box plots instead, because box plots do show us our data in a pretty different way, but we're going to be answering some similar questions. So here's the situation. When anthropologists find steel artifacts, they can test the amount of carbon in the steel to learn about the people that made the artifacts. Here are some box plots showing the percentage of carbon in samples of steel that were found in 2 different regions. So we can see that the top box plot is showing region 1 and the bottom box plot is showing region 2. So first we're going to answer, was there any steel found in region 1 that had more carbon than the steel found in region 2? Remember that when we're reading a box plot, each little section of it represents a quarter of the data, or 25%. Pause, get your answer to this question, and then listen to mine. So when I'm answering this question, I'm thinking about that since each of these sections represents a quarter of the data, that tells me that if you look at the maximum value of region 2, at least 3/4 of the data from region 1 was greater than even the maximum of region 2. So a lot of the data from region 1 had a greater amount of carbon than the steel found in region 2. Let's look at the flip side of this question. Was there any steel found in region 1 that had less carbon than the steel found in region 2? So again, pause, take your shot at doing the problem, and then listen to mine. So what we already said was that at least 75%, or 3/4 of the steel in region 1 was greater than any of the steel found in region 2, because all 3 of these sections are greater than any part of region 2's graph. But we also know that a quarter of the data from region 1 lies in this area off to the left, and we know for certain that there was at least one that measured between 4/10 and 44/100, so maybe 41/100 or so, which is less than at least all of the data in these 3 sections of region 2's graph. So that tells us that at least one data point from region 1 was less than 75%, or 3/4 of region 2's data. So yes, there was at least some steel found in region 1 that had less carbon than the steel found in region 2. What we don't know is how spread out any of the data in this section is. Is it kind of evenly spread out here? Is it mostly down here near this minimum? Or is it just one piece of steel that was at this minimum value and then the rest of it was up here all greater? We can't really tell how it's spread out within that region of the graph. We just know that a quarter of the data is there and that there's at least one value that fell down here. So then, based on what we've already thought about, is there a meaningful difference between the steel artifacts found in region 1 and region 2? And how do we know? So again, pause, try to answer it, come back. My answer to this one has to do definitely with those quarter sections of the data in each graph. Going back to how we answered the question here about was there any steel in region 1 that had more carbon than the region 2, we said that at least 75% of the data in region 1, or again, 3/4 of the data found in region 1, was all greater than any of what was found in region 2. To me, that means that yes, there is a meaningful difference. Another way we could think of this is, would we guess that the people who made these two steel artifacts could have come from the same exact, let's say, town or village or wherever it is, or city? Could they have come from the same place based on the data? And if we look at this data, most likely you would guess that these two regions were probably not all that similar. Again, based off of that, so much of the data in region 1 is greater than all of the data in region 2, while the data in region 2 all falls in or below the bottom 25% of region 1. So to me, that means that yes, there is a meaningful difference. So what you should hopefully be taking away from this today is that you can compare data sets even if there's overlap. And part of what we have to do as the mathematicians is decide, are the differences between those two data sets important? Do they matter? Do they communicate to us that there is some difference? Like here, we can see that there's a lot more carbon in the steel in region 1 than in region 2. So if we know something about what carbon in steel means, we would probably guess that there's some big differences maybe between how their steel was made or how old those tools are. If we were to go back to the graphs about the backpacks, we would probably guess, if we knew nothing about middle schoolers and high schoolers, we would still probably guess that for whatever reason, 10th grade students have to carry a lot more in their backpacks, which as middle school students and myself a middle school teacher, I know that that's probably true because the high school classes might have to carry more books for their classes, while middle school students might keep them in the classrooms. So that might explain why 7th grade backpacks tend to weigh a fair amount less than 10th grade backpacks. So we can use different data plots not only to compare, are the differences meaningful, but also to try to understand more about the samples that were surveyed and the populations that they represent. That's all for this today. Thanks for watching, guys.